Yeah, thanks for having me today to give an update on Lunar-VISE. Lunar-VISE is the Lunar Vulcan Imaging and Spectroscopy Explorer, which was a PRISM mission that was selected as part of NASA's second PRISM call to specifically land at the Gruithuisen domes. And so for our 10-day science investigation, 10 Earth Day science investigation, we're going to really be looking at understanding and addressing questions about how these silicic volcanic features formed. And so we're going to do that by having one overarching science goal. And that science goal is to really understand how silicic volcanism works at the Gruithuisen domes. And then use that and apply that to the other silicic features that we see across the lunar surface. We also have one exploration goal, which is to understand the geotechnical properties of the regolith across the domes, and also understand how that is affected when we have a lander landing and a rover interacting and moving about the dome. Oops, whoa. Well, you got to see my whole talk. Okay. Okay, so to accomplish our science investigation, we really want to map the composition of the domes as we move about the surface. So we want to look to see what the composition is and if it varies across the surface. And if we do see any variations, we do want to link that to any surface morphologies or geologic features or any textures that we see in the scene. Specifically, we're going to be doing that with two different techniques that are independent of one another, but also are really nice complements to one another. And so we'll be looking at composition using visible near infrared as well as thermal infrared spectroscopy and also gamma ray and neutron spectroscopy. And then we'll also want to take what we learn at the domes and allow us to ground truth or calibrate all of the orbital data sets that we already have in hand, because that will allow us to take what we've learned at the domes and apply that to other silicic features. Okay, so to do this, to map composition, we're going to be using a suite of instruments on a rover. And so we have two key instruments on the rover. We have LV-VIMS, which is comprised of two separate cameras that are bore-sighted and placed on a single rotation stage. And so these cameras can rotate about and take a 180-degree scan as we get to each rover waypoint. And then we also have a gamma ray and neutron spectrometer that will be located on the other side of the rover. And we'll be using the GRNS to take measurements as we rove, but then also do dedicated integrations at every rover waypoint. You'll notice that we have a very simplistic design here for our rover, and that's because we're still waiting for our CLIPS provider to be selected. And so these are just stand-ins for the actual rovers, and you'll later see my very simple lander later. If we assume that LV-VIMS is mounted at the top of a 1-meter rover, we should have sub-centimeter spatial resolutions with both of our cameras, multispectral cameras, at distances at about 3 meters in front of the rover. Okay, so just a bit about the two instruments or the two multispectral cameras that comprise LV-VIMS. First, we have a multispectral visible and near-infrared imaging camera, which we call LV-VIC. LV-VIC has 7 spectral channels, which you can see here. You'll note that most of those look very common to you because these are spectral filters that have already flown on things like Kaguya and Clementine and LROC WAC. And so again, we'll be able to take our surface measurements and directly correlate those to the orbital data sets that we already have in hand. The LV-VIC will be mostly looking for mafic bearing minerals. So we'll be using this to identify any iron bearing materials that we see across the dome and kind of setting an upper limit for how much iron we would expect to see on the dome. We'll also, along with LV-VIC, have LV-Cirrus, which is our multispectral radiometer. LV-Cirrus has 3 spectral channels and 1 wide-range thermal channel. And so this will allow us to do both composition, but then also thermophysical properties across the dome. We have 3 channels that were specifically chosen to map the Christensen feature for highly silicic materials. But these channels do overlap or are similar to channels that are flown on Diviner, as well as the Lunar Thermal Mapper on Lunar Trailblazer. And so we'll have good overlap between what we'll be measuring at the surface and being able to relate that to orbital data sets. Okay. Also on the rover, as I mentioned, we have a gamma ray and neutron spectrometer. The GRNS is comprised of 2 different sensors. We have one click sensor that has a diameter of 2.5 inches, which will be used for collecting gamma rays. And then we also have a 2-inch diameter click sensor that will be used for the neutron detector. These will be used to map thorium across the dome, as well as major elements. And for those that are interested in hearing more details about this, tomorrow afternoon, the PI of the instrument, Craig Hargrove, will be giving a talk in tomorrow's afternoon session. As I mentioned, we also have an exploration goal, and that exploration goal is really to understand, is the regolith at these silicic features different than the regolith that we see in the highlands as well as in the mare? And how does that regolith behave as the rover and the lander is interacting with it? If you want to know a little bit more about our exploration goal and how we're going to go about this, there's a poster this afternoon by Ben Byron, who's going to go into how we'll be using data from the rover as well as the lander to get at these geotechnical properties of the regolith. But we will be specifically using the cameras on the lander to achieve these exploration goals. We have 2 cameras, one the descent camera, which will be located at the bottom of the lander. So this will be a nadar facing camera that will be collecting data as we land. So it'll allow us to map the geology of the landing site, as well as understanding how the lander affects and scours the surface and how dust is lofted and how long that dust stays lofted. We also have a context camera that will be sitting at the top or on the side of our lander. The context camera will have the ability of doing 270-degree scans. This is essentially the same camera as our multispectral camera on the rover, except that we don't have filters on it. So we won't be getting multispectral data, but it'll be the same data set, camera speaking wise. And so this will allow us to get a geologic context of the landing site throughout the lunar day under different illumination conditions. And we also have the capabilities of taking movies as the rover is moving about. So again, we can track how the rover wheels are interacting with the regolith, how material is being kicked up, if it's being kicked up at all. And again, really addressing how the rover is interacting with the regolith. We have chosen a landing site for our mission. We will be landing on the Gamma Dome. Specifically, there's a green box here that's outlined kind of on the plateau edge of the Gamma feature. You'll see this area in detail here on the left. We selected this landing site for several reasons. One, we wanted to minimize roving distance to boulders and undisturbed regolith, because to accomplish our science objectives, we really need access to both boulders and undisturbed regolith. But we also wanted to minimize hazards, so things like slopes greater than 10 degrees, boulders, and large craters. And so this landing site was selected for this because we do see this small fresh crater. So this diameter. This crater is about 120 to 150 meters in diameter. And you can see in the image that a large boulder field has been kicked up. And so having access to this boulder field is really key for our science investigation. The team has been working on developing a notional design reference mission and thinking through what measurements we need to be able to achieve our science objectives. And so how do we get to the boulders and enough boulders in our 10-day science mission so that we can address our science questions? We also like this landing site location because it gives us access to the edge of the plateau. And so we can go and look at a distance and we'll be able to get observations of the Delta Dome as well as the mare surrounding. So we'll get some nice context data to go along with our measurements of the Gamma Dome. And if you're interested, there'll also be a poster this afternoon by Pierre Williams, who'll be going over in detail kind of our thought process and how we've developed our notional design reference mission and characterized the landing site. So where are we today? We are currently building instruments. So we our instruments are currently under development. We have individual components that have been built and are undergoing functional testing and performance testing. We did pass our critical design review in late January, early February, and we also passed our key decision point review in March. And so we're just building instruments. The science team is busy continuing to characterize the landing site and really developing a way to make sure that we have a very flexible operations plan when we get to the surface so that we can collect as much data at the dome as possible for everyone here in the room. So with that, thank you.
Well, you have
Thank
time.
you.
Thank you. So you have time for Kerri. Please ask questions about Gruithuisen domes. One waiting for somebody else, maybe. So you're not too much afraid about the trafficability on the dome, on the Gamma Dome?
To be able to really understand and measure the composition of the dome, we felt that we needed to be at the surface of the dome. And luckily, because it is a highly silicic feature, the plateau is actually really pretty flat. And so it was pretty easy to find areas that had low slopes. And we investigated several areas with trying to minimize boulders and small impact craters. And we saw similar numbers to had we landed on the mare surrounding. So yeah, it's exciting to say that we're landing on the dome, but it's pretty safe where we're going. So.
One more.
Barbara Coy, Nessa Goddard. Just related to that, do you expect the geotechnical properties to be similar to other highland sites or different, given it's a different lithology?
Yeah, so Paul Hain had his paper looking at the thermal inertia using diviner data. And initially that data suggested that perhaps the thermal physical properties of the domes were slightly different. Although we've had recent follow-up investigation using diviner data from Ben Byron suggesting that maybe it's not different. And so that's something that we want to test is the regolith different? Do we have to worry about where we're landing on the lunar surface to think about tools and wheels and all these things? And so I think that will be a really nice test when we get to the domes.
One more. Yep, one more.
Just if I may have missed this, I hope not. What limits your observing time to 10 days?
It's just the length of the lunar day. And so it's 10 Earth days. And so for Prism 2, there were not survive the night capabilities. And so we just have a lunar day to work with. And we're accounting for the fact that when we land at the surface, the lander provider will have some amount of checkouts at the surface that they'll need to do and get things charged up before the rover can come off and start doing activities.
Thank you.